Here in 9.10, we have the kind of the dual ideas of a smart pointer and memory leakage. Now, any of us that have ever used, I'm going to pick on Chrome here because Chrome is the king of doing this. Chrome will allow things to run in the background, but it does not always do such a phenomenal job of deallocating that memory when, for example, a tab closes or a tab is, especially if a tab is crashed. So what ends up happening is Chrome says, okay, here's, a few dozen megabytes that I need to be able to load a page. Now, here's another few dozen megabytes that I need to be able to load a page that you've got in another tab and another tab and another tab. And what ends up happening is you end up with, 17 active tabs in Chrome. And all that while, we've got advertisements being loaded in the background. We've got JavaScript running in the background. And all of those things are, in fact, waka, 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 like Pac-Man chewing on memory, on storage allocations as we go on. If you close a tab and that memory is not deallocated, it's not destroyed, the references are still out there, even though you have that tab being closed, we still don't have access to the few dozen, meg of RAM that were allocated to that tab. Now you close another tab, now we've got 50 megabytes of RAM that are not allocated for other things. We close another tab, 75. And it keeps doing that. And sooner or later, if you don't kill Chrome or restart your system or do whatever it is that you need to do to get away from that, you're looking at, why is my one instance of Chrome chewing up 7, out of 12 gigabytes of available RAM? Well, because it's leaky with memory. It allows memory to not be recaptured. And then, it's in the wild. It's unrecoverable at that. So what we have been doing with pointers here through chapter 9 is all in an attempt to be as parsimonious as possible with space allocations, so as careful as we can with memory, but we're still not quite there. The idea that we see here in 9.10 with a smart pointer is kind of the next step that we saw in 9.9 with dynamically allocated references. So instead of using new and delete and being, the entity in charge of remembering to dereference and destroy a reference to an object that is no longer being used, let's rely on C++ to be able to do that. And we do that with a unique pointer. Now, I'll tell you, for right now, I am pleased if you're okay with the idea of a unique pointer. A shared pointer, I'm just going to read to you what it says here so that you can kind of hear it from a third party. I'm the third party. But what I'll tell you is that doesn't really come up in any of the work that we can demonstrate. And a weak pointer certainly doesn't come up in any of the work that we can demonstrate. I would consider, the idea of a weak pointer to be something that, you wouldn't see again through many years of your development career or until you go seek like a master's degree. Really, that's where my exposure to weak pointers came through, was, my capstone class in graduate school. So I don't want to burden you with that stuff now because you won't use it. But a unique pointer is the sole owner of a piece of dynamically allocated memory. So a unique pointer owns that reference. It owns the spot. The however big the allocation is. No two unique pointers point to the same piece of memory, and when a unique pointer goes out of scope, so if we create a unique pointer inside of a method call, once we leave the scope of that method, it is automatically destroyed and reclaimed by C++. No further action needs to be undertaken on your behalf to reclaim that memory. So what that does is prevent a leak from happening there. So if you know you are just doing some sort of display work with an array, if you know that you are, you're taking large sets of data and you're moving them down to smaller sets of data, and then you're going out to a file, for example, that's a really good use of a unique pointer, because once you are done doing the work, like reading the values and storing them in a file, you just allow C++ to deallocate and destroy the references to that, and then reclaim all of that available space. And it turns out to work pretty well.